And now we are going to example number 6, sizing plug flow reactor in series. Using the data in table 2.3, calculate the reactor volume B1 and B2 for the plug flow sequence in series when the conversion in the first reactor is 40% and the final conversion is 80%. The entire molar flow rate is the same as in previous examples and is equal to 0.4 moles per second. So here we have the table 2.3. In the first row we have X, the conversion that goes from 0.0 to 0.8. And in the second row we have FA0 divided by minus RA that goes from 0.89 to 8.0. In addition to graphical integration, we could have used numerical methods to size the plug flow reactor. In this example, we shall use Simpson's rule from the appendix A/4 of our book to evaluate the integrals. The Simpson 3-point rule, we must recall that is the integral of fx dx is equal to delta x divided by 3 times fx evaluated at 0 plus 4 fx evaluated at fx1 and f evaluated at x2 with the limit from x0 to x2, and for the first reactor x0 is equal to 0, x1 is equal to 0.2, and x2 is equal to 0.4, and delta x is 0.2. So here the volume will be equal to FA0, the integral of dx divided by minus RA. So this is going to be delta x divided by 3 times FA0 divided by minus RA evaluated at 0 plus 4 times FA0 divided by minus RA evaluated at 0.2 plus FA0 divided by minus RA evaluated at 0.4. If we use the appropriate values from the table 2.3, we will have that the volume of the first reactor is going to be 551 cubic decimeters or liters. And for the second reactor, B2 is going to be FA0 integral of dx divided by minus RA, but now the limits are going to be from 0.4 to 0.8 because that's the final conversion that we want. So here it's going to be delta x, the volume B2 is going to be delta x divided by 3 times FA0 divided by minus RA evaluated at 0.4 plus 4 times FA0 divided by minus RA at 0.6 evaluated plus FA0 divided by minus RA evaluated at 0.8, and substituting the values of the table 2.3, the result will be the volume to 1,614 cubic decimeters or liters. So the total volume, which is the volume, the sum of these two, is going to be 551 plus 1,614 liters. So this is going to be 2,165 liters, which is the same volume we calculate for a single PFR to achieve 80% conversion in example 4. So here we see that for PFRs, we have the same result in a big volume, in a reactor of big volume, if we compare with two reactors which sum is the total volume. So one reactor of the sum of these two reactors, the volume of these two reactors will give us the same result. Example 7, an adiabatic liquid phase isomerization. The isomerization of N of butane was carried out adiabatically in the liquid phase, and the data in table E2/7.1 was obtained. So here we have again in the first row the conversion X that goes from 0.0 to 0.65, and in the second row we have the rate minus RA that goes from 39 to 25. So here we have the reactors. The first reactor, a CSTR, in which we achieve a 0.2 conversion. A second reactor is a PFR, from which we can get a 0.6 conversion. And the last reactor, a CSTR, from which we get a 0.65 conversion, and they are placed in series. We are going to calculate the volume of each of the reactors for an entering molar flow rate of N-butane of 50 mole kilograms per hour. Solution. Taking the reciprocal of minus RA and multiplying by Fa0, we obtain the following table, E2/7.2. So here we have Fa0 divided by minus RA is equal to 1.28 when minus RA is 39, and Fa0 divided by minus RA is equal to when minus RA is equal to 25. So here for the first CSTR, when X equals 0.2, then Fa0 divided by minus RA is equal to 0.94 cubic meters. From here, B1 is equal to Fa0 divided by minus RA times X1. So it's going to be 0.94 cubic meters times 0.2. This is equal to 188 liters. For the PFR, B2 is the integral of Fa0 divided by minus RA dx with the limits from 0.2 to 0.6. So here we again use the Simpson 3-point formula with delta X equals 0.6 minus 0.2 divided by 2, which is equal to 0.2, and X1 is equal to 0.2, X2 0.4, and X3 is equal to 0.6. So the volume is going to be the integral of Fa0 divided by minus RA dx, which is equal to delta X divided by 3, Fa0 divided by minus RA at X equals 0.2, plus 4 times Fa0 divided by minus RA at X equals 0.4, plus Fa0 divided by minus RA at X equals 0.6. If we substitute the values from the table, we will get that the volume 2 is going to be 380 liters. So, for the last reactor, which is the second CSTR, the mole balance will be in minus out plus generation equals 0. Fa2 is the molar flow rate coming from the second reactor, minus Fa3, which is the molar flow rate leaving the last reactor, plus Ra3, B3 is what is generated in this last reactor. All that is equal to 0. B3 is equal to Fa2 minus Fa3 divided by minus Ra3, and Fa2 is equal to Fa0 minus Fa0 times X2, and Fa3 is equal to Fa0 minus Fa0 X3. So If we rearrange this equation, we will have that the volume 3 is equal to Fa0 divided by minus Ra3 times x3 minus x2. So having the value from the table, we will have that B3 is equal to 2 times 0.6, which is x3, minus 0.65, sorry, which is x3, minus 0.6, which is x2. That will give us 100 liters. And here we have the Leven's-Field plot for the three reactors. For the first reactor, we have the rectangle from 0 to 0.2 and with the height of nearly 1. And from the second reactor, we have the area under the curve that goes from 0.2 to 0.8. And for the third reactor, we have the rectangle of 0.6 to 0.65 and the height of 2. And that will give you the total volume. Example, reactor space-time and space velocities. Say, calculate the space-time tau and space velocities for each of the reactors in examples 2 and 3. Solution. For example 1, we recall the entry volumetric flow rate was given as 2 liters per second or 0.002 cubic meters per second. And we calculate the concentration and molar flow rate for the conditions given to be CH0 equals 0.2 moles per liter and FA0 is 0.4 moles per second. For example 2, the CSTR volume was 6.4 cubic meters and the corresponding space-time and space velocity R. Tau equal the volume divided by the volumetric flow rate, so it's going to be 6.4 cubic meters divided by 0.002 cubic meters seconds to the minus 1. That will give us 0.89 hours. And space velocity, which is the inverse, will give us 1.125 hours to the minus 1. For example 3, the PFR volume was 2,165 liters or 2.165 cubic meters, and the corresponding space-time and space velocity R, tau, equal the volume divided by the volumetric flow rate, so it's 2.165 cubic meters divided by 0.002 cubic meters seconds to the minus 1 will give you 0.30 hours, and the space velocity, the inverse, will give us 3.3 hours to the minus 1.